And we're back. So we're going to continue with the balance of our module on regularization and then jump right in to validation. But we won't do the entire module on validation. We'll save finish that off on Tuesday, the 31st of March. And so administrative, the reading, all of this in the sequence about handling noise is from chapter 4 in the book. You should be following along. Section 4.1 is on overfitting, section 4.2 on regularization, and 4.3 on validation. Homework 3 is due this Tuesday at the usual 1 second before midnight, 11:59, 59 seconds, on the 31st of March. So hypotheses have regularizers, and in alternate treatment, we can call the regularizer omega. And so we add this regularization term, omega of h, and it's specific to the hypothesis, and we draw or pose an augmented optimization problem where we add to our expression for in-sample error this regularization penalty. So this is specific to the hypothesis because it involves the weight vector, W transpose W, lambda upon n, and so therefore it's very specific to the hypothesis. Now this looks a little bit like something we've seen when we talked about the VC bound. In the VC bound, when we talked about complexity term that we added to our expression for in-sample error, this was defined over the hypothesis set. And we said that out-of-sample error is bounded from above by in-sample error plus this complexity term. And so this augmented error, we're saying, is better. It kind of acts like out-of-sample error. It is better than E in as a proxy for E out. Now, because the augmented version of error, E in plus our regularizer, because it considers the complexity of functions, it's better as a proxy because of its ability to produce smooth solutions. And if you think about what happens as you're searching through the space of hypotheses for a final best hypothesis, you can take very jagged paths that wander as you're trying to get closer and closer to something that you hope would mimic out-of-sample error, or the ground truth target function, which would minimize out-of-sample error. You take a smooth path, it's kind of more direct. It doesn't kind of wander off. It wanders or moves in a path that is directed towards this final best this target function, and therefore in the direction of minimizing out-of-sample error. Okay, so let's take a look at choosing a regularizer. And so when you choose a regularizer, the selection criteria for what you're doing should represent solutions that are in the direction of the target hypothesis. They don't wander away or wander around aimlessly in a hypothesis set, potentially diverging away from your target function. It is in the direction towards your target function. And so in general, it's said that smoother paths are simpler. They're not wandering, and as such, they're more so in the direction of the target hypothesis or the target function. If you have a poor choice of your regularization term, omega, your regularizer, you can absolutely minimize the effect of this poor choice. Maybe you choose one that's not in the direction of target hypothesis. You can minimize the impact of this bad choice of regularization by setting a small value for lambda. So that's kind of a good thing. If you make a bad choice, you can minimize the impact of that bad choice. And so in a neural network, there's a regularizer that looks like weight decay. And that can have some very beneficial qualities. And in essence, when you have your neural network, the set of possible weights are all of the networks for all of the layers, from all the inputs to all of the nodes in each layer as you go up from layer 1 up through layer big L. Now, with weight decay, it's based on the observation, and we'll look as an example at the nonlinearity, the tanh function, which is in the blue. Now, tanh implements both nonlinear behavior, something that looks like a hard threshold, as your signal your score, that weighted sum, is higher in magnitude, be that on the positive side, or on the negative side. So let me select a pen here, and I'm going to select magenta, since it's a different color from everything I have. So when we take a look at this tanh function, that's in the blue, if the score, the weighted sum, is very large in magnitude, both positive and negative, the tanh function acts a lot like a logical operator. It's either +1 or -1. If our score is smaller in magnitude, closer to 0, well, it looks a lot like a linear function, this linear operating regime. And so eventually what happens as your weights get smaller, we talked about the update function as being weight decay. They get smaller and smaller and smaller as those weights get smaller, the signal gets smaller and smaller and smaller. And in a neural network, well, if your weights get smaller, maybe you should get rid of a few of them. And so there's a penalty term that's used or can be used in neural networks called soft weight elimination. And what it says is that if your weights get smaller, you tend to be more in the linear regime. And if you have a neural network where your nodes at one layer, let's say there's a linear behavior in their nonlinearity, and they go to nodes in another layer, and that's linear, and then you go to nodes in another layer, and that's linear. So if they're all linear, effectively, it's just one big linear operator because it's linear at every step, and it doesn't really add much to have linear everywhere along the way. So therefore, since small weights give you this linear behavior through this nonlinearity, this tanh function, it would be good to say, all right, well, if weights get smaller, just eliminate them altogether. Set them to 0. Let them drop out. And that has other benefits in a neural network. Essentially, if your weight goes away, goes to 0, you can think of that as inducing a smaller VC dimension because you now have one less weight, and therefore the complexity of your model is smaller in the VC dimension sense of it. And so what does the soft weight elimination penalty term look like? Well, this is our omega. It's for a particular hypothesis. It's a particular setting of weights. It's the sum, and we have a Wij superscript L for all the inputs, all the nodes in a layer and all the layers. We square those weights. Now, in the denominator, we have this term, this beta. And essentially, if Wij gets very small, this beta term dominates and it drops out. So that weight is now 0 or less emphasized. It goes to 0. Its impact is 0. And so in essence, it would prefer, if you have a penalty term like this, to set that weight to 0 because this denominator, that beta, is going to cause its impact to go to 0 if W is small. Let's contrast that if W is large, what happens? Well, if W, the weight, Wij superscript L, a particular weight, is very large, what happens? Well, if it's very large, we square it, and it's going to dominate this beta squared in the denominator, and therefore this is going to be closer to 1. So in essence, what this does, it partitions your weights, all of your weights in your neural network, into two groups, the meaningful weights and the non-meaningful weights, the important weights that matter, those for which Wij is large. And then as weights decay, if they get small enough, it's going to prefer, because this is a penalty term, to select weights such that those particular ones that are small, since it needs to minimize the expression of En plus this complexity term, those particular weights that are close to being 0 or very small are going to drop out because those are the preferred weights for those particular weights in your network to minimize the expression that includes this penalty term. And so big weights end up being left alone with this weight decay penalty for neural networks, and small weights are pushed to 0 for a given beta. And so there are two different ways you can mitigate complexity in a neural network. You can impose a smoothness constraint, and we talked about that with regularization, or you could also impose an elimination strategy with your penalty term, your regularizer, and that will cause small weights or less important weights to drop out, and that gives you a better VC dimension, a smaller VC dimension, because you have fewer effective parameters. Okay. So let's take a look at early stomping. Now, certainly, if you're going to optimize, including a quantity such as this weight decay, you want to put that quantity to be minimized in the objective function. You could do this early stopping through validation, or you could do it through the objective function. Let me correct myself. So if you put this early stopping in the objective function, that's a bad mistake, right? So you say, okay, well, what is my out of sample error? You can certainly estimate that by setting aside some data, and then each time you run a batch round of your forward pass and run back propagation for each epoch, you then furnish this set aside data, and then you estimate out of sample error. Now, certainly in your objective function, you could do something like that, but it'd be kind of awkward. It's something that really belongs in validation, not in optimization. So things like smoothness constraints would certainly go in your objective function, but something having to do with early stopping is really better suited for in validation. And we'll talk about validation in the next module. So in the book, they ran an experiment, and this takes a look at the impact of regularization on two sources of noise: stochastic noise, we have that graph on the left, and deterministic noise. And as we said before when we talked about regularization earlier, we said that, or noise rather, stochastic noise and deterministic noise have the same impact, or you see the same behavior on your out-of-sample error. Now, in the graph on the left, we have stochastic noise, and along the horizontal axis, we have the regularization parameter lambda, and on the vertical axis, we have the expected out-of-sample error. Now, each one of these lines represents a different amount of stochastic noise in the ground truth target function. And remember, we're sampling data points from this target function. And so as you increase the regularization parameter lambda, you're turning up more and more the impact of that constraint, and that boils down to that soft weight budget being smaller. So lambda increases, the weight budget gets smaller, which ends up giving you smaller weights, which makes the model that you choose from your hypothesis set smoother. So as you increase the regularization parameter with no noise, okay, well, you start to underfit because there's no noise, and because the model gets too simple or too simplistic or too smooth, and you underfit, so your expected error starts to increase. But let's see what happens. We don't need any regularization. The best regularization parameter is 0 if you don't have any noise, any stochastic noise in your ground truth target function. But let's take a look when you have a little bit of noise. So sigma squared is 0.25. Now, with no regularization, well, what happens? Our expected E out is high, and then as you increase the amount of regularization, our expected out-of-sample error starts to decrease, and you notice when we go from 0 noise to 0.25 sigma squared, the regularization that we need is higher. It's no longer 0, right? Something just a little bit bigger than 0.5, like 0.55. And so as we increase the amount of noise, say to 0.5, we're going to need more regularization, right, to deal with that increased stochastic noise. And so in this case, at 0.5, we still have a higher amount of expected out-of-sample error, but then it starts to come down to a reasonable amount with even more regularization. So here, lambda is bigger than 1. So as you increase the amount of stochastic noise, you need a larger amount of regularization as our regularization parameter gets bigger. Likewise, we see the same type of behavior when it comes to deterministic noise. And so here we have a degree 15 non-noisy target function, and we have no regularization. And as we increase the amount of regularization, we don't really need any in this case, but if you increase the complexity from 15 to 20 degree polynomial target function, you have a much higher expected out-of-sample error with no regularization, and you'll see E out, expected E out, get smaller as you turn on some regularization. And so that smoothness constraint is having an impact in reducing the expected out-of-sample error for that more complex, it's twice as complex target function, degree 30 polynomial. So then we take a look at this red curve, and that corresponds to our degree 100 polynomial target function. And as we increase regularization, we see that the expected out-of-sample error gets smaller and smaller and smaller, and eventually we reach a good point where it's no longer, it's a good value before it starts to underfit a little bit. But we see here we need a bigger value for the regularization parameter lambda. And so this is to illustrate that deterministic noise, as far as deterministic noise and stochastic noise is concerned, regularization parameter has the same effect on these two different sources of noise. Now recall when we talked about stochastic noise and deterministic noise, we said that the model performance due to these two sources of noise is similar, but also regularization has the same effect regardless of whether it's stochastic noise or deterministic noise. Okay, so we're going to end there. Again, we have some reading, but let's change gears now. Validation. So last time we talked about regularization, and we developed this solution for a regularization parameter, and this was an expression that had a direct correspondence to a soft weight budget C. And so we expressed geometrically the relationship between the constraint and the expression for in-sample error, and we showed that the best solution is one where the direction of the constraint was in the opposite direction of the gradient with respect to En. And so from that, we developed an expression for the gradient, and we effectively took the derivative to get the original, to come upon an expression that was the equivalent unconstrained version of the optimization problem that had the constraint of W transpose W is at most C, the weight budget, that soft budget. So we then took this expression and in feature space, through a mapping to a polynomial, because we wanted a polynomial hypothesis space, we minimize this by setting the gradient of this expression in vector matrix form to 0, and then we solved and arrived upon something that looks a lot like pseudo-inverse, where the difference between this regularized version of regression and the non-regularized version WLin is this term involving this, let me select a pen. The difference between the regularized and non-regularized version is this term involving this lambda I. And so as such, if we increase lambda, what happens? Well, if we increase lambda, that makes this term bigger, and since it's an inverse, that makes this expression smaller, and we end up getting a smaller set of weights, a smoother solution. If this term is smaller, well, this term ends up being bigger, right? This term ends up being smaller. If this term is smaller, it's in the denominator, so this result ends up being bigger, and we get larger weights, i.e. a less smooth solution. Whereas WLin always tries for the minimum solution to in-sample error, regardless of how smooth or non-smooth those set of weights might be. And so as such, we're introducing constraints, and this lambda is inversely proportional to that soft budget C. As lambda increases, C decreases, equivalent. If lambda is decreasing, smaller, that corresponds to C being larger. So that's where we left off last time. We also just got done with the learning curve, showing that regularization behaves the same regardless of the source of noise, if it's stochastic noise or if it's deterministic noise. Okay, so let's consider the difference between validation and regularization. And so for validation, for regularization, we added to in-sample error an overfitting penalty. And this augmented version of error is a good proxy for out-of-sample error. Now, for regularization, we added this penalty, we estimated this quantity, and determined that it gives you a smooth solution, and that smooth solution brings you closer to this ground truth target function, in the direction of the target function. But with validation, it's a little bit different. Rather than saying E out is E in plus some other complexity measure, and you're doing this estimate of the overfit penalty, with validation, it takes a direct approach, and it tries to estimate out-of-sample error directly. So let's explore this idea further, and let's do an analysis of E out. And let's do an analysis of E out, our out-of-sample estimate. And so the error on an out-of-sample point is just E, pointwise error, of the difference, pointwise error between the hypothesis, H of X, on that out-of-sample point, and your ground truth label, Y. Now, of course, there are different error functions that you can use, like squared error, as we did with regression, or binary error, which is the 0-1 loss function. And if you were to take the expectation with respect to all your data points X, drawn from the probability distribution that governs the features that you encounter out of sample, that's just the expectation of this pointwise error between H of X on that out of sample point and Y. Now, that's nothing more than out-of-sample error for that particular hypothesis. And we can take that quantity, that pointwise error, we can also measure the variance of it to tell us how much it'll swing up and down across our data set for the hypothesis. So if we compute the variance of this pointwise error between our hypothesis H of X on these out-of-sample points and our ground truth target function label, we get sigma squared, right? We'll just call it sigma squared. It's some variance. Okay. Now remember, this isn't the same variance that we talked about when we talked about stochastic error. This is just variance of this pointwise error out of sample on out of sample points. Okay. So let's now take this idea of the expectation of the out-of-sample error for some hypothesis on a single out-of-sample point, and let's carry this to a set of out-of-sample points. And we're going to call this set our validation set. And we're going to introduce a little bit of more terminology. And this K, capital K, is the size of this validation set. So we have a set of data points, K many, big K many, out of sample, X1, X2, X3, up to and including XK. And each one is associated with a ground truth label given by the target function. So if we wanted the error associated with these out-of-sample points comprised of which your validation set is comprised, we would compute the following. We say eval, our validation set for the hypothesis, is just the average pointwise error. So eval is 1 upon K. The sum, K goes from 1 to big K, of this pointwise error between your hypothesis evaluated on each point out of sample from this validation set and their respective ground truth class labels, Y sub K. So if we were to take the expectation of this validation set, well, we'd just take the expectation of eval. What is that expectation? Well, we take the expectation of this sum, the expectation of a scalar, we can just pull that out due to linearity of expectation. Then the expectation of a sum is the sum of the expectations. So we bring this expectation inside of the summation, and we had this result from before, the expectation of a single pointwise error on a single out-of-sample point, that's just E out of H. Okay. So now, in this summation, E out of H is a quantity, it's a scalar, and we sum this with itself K many times, and gives us K times E out. We multiply by that leading 1 upon K, and that gives us E out. And there's our solution. So if we're going to take the variance of this eval, one of the things we want to do is we want to know, on average, what is validation error for this set of out-of-sample points, not just a single out-of-sample point, and what is the variance, because we want to know how bad this can get. So in similar fashion, we're going to compute the variance of eval of h. So the variance of this expression up here. So if we take the variance of eval, well, we know that the variance of a scalar is squared when we take variance. So we're going to have a leading 1 over k squared, it's this term, and then the variance of the sum is the same as the sum of the variance. So we bring this variance inside the summation. So now we have 1 over k squared, the sum, k goes from 1 to big K, of the variance of a single point-wise error of this hypothesis on a single out-of-sample point. So we had this expression before, and when we did that, we called it sigma squared. So now sigma squared is a constant, it's a value, it's a scalar, and we're going to sum sigma squared with itself k many times because of the summation. So we write a big K there, and now we have this leading 1 over k squared. Right? We do a little algebra, we're left with this solution, sigma squared over k. Now, of course, this is the variance, but if you take the standard deviation of it, the standard deviation is just the square root of that. Well, if the square root of this expression, we take the square root of the numerator, sigma squared, over the square root of the denominator, big K, that's just sigma times 1 over radical big K. Now, of course, sigma is a constant also. And so if we were to look at the validation error, eval, right? Eval is nothing more. Eval is nothing more than E out on that hypothesis plus or minus some deviation. Now, of course, that deviation is going to be proportional to the size of the validation set. And since that sigma is a constant, and we don't care about constants in big O notation, so we're going to write 1 over radical k. Okay? So what does that say? That says that the validation error is going to be equal to the out-of-sample error plus or minus some fudge factor that's dependent on the size of the validation set. And so at the outset, what we're doing is we're taking some of our data and we're setting it aside. And because your model has not trained on that set aside data, you can treat that set aside data as if it were out of sample. And then you take that set aside data and you use it to estimate your out of sample error by just running your final best hypothesis on that set aside data. And with this, we've shown that that so-called validation error is a very good estimate for out-of-sample error. And that estimate gets really, really good as k, the validation set size, gets bigger and bigger and bigger. And that kind of makes sense, right? So if you took all of your data points and used them for validation, you're going to get the absolute best version of out-of-sample error that you can, because k is going to be as large as possible, and therefore this deviation is going to be smaller. Okay, but there's a complication. It's not that simple. And we'll talk about this tension between two competing factors as it pertains to validation set. So let's take a look at what this validation set is. You're given an original data set, D. So let's call this D your data set. And now you're going to take D, which is your in-sample data, in-sample, and you're going to carve out of it some subset of your data containing your k many in-sample points. So you take this validation set of size k, so k examples with their class labels, and then the remaining data points in your data set is now what you're going to treat like your training set. Training set. Now, this validation set, if that's of size k, and your original sample size has n many data points in sample, that means what's left in your training set is n minus k examples. So let's introduce a little bit more notation. If D is your data set, D val, subscript val, are those k many data points that you're going to set aside for validation. And then the remaining data points, n minus k of them, those are going to be your training set. That's what you're going to use to train your model. So these will be treated like your in-sample points that you're going to use to train your model. And then these, you're not going to train on. You're going to furnish it to your final best hypothesis G, and these are going to act as if they were out of sample. And out of sample. Now, because your model has not trained on those data points in the validation set, it's going to behave as if it were your out of sample data. And the resulting error that you get, that's your eval. And we just saw that there's a relationship between eval and eout that gets better. Eval gets better as an estimate for eout if k is quote unquote suitably large. But the problem stems from the following, that if you make k very, very big, you're basically robbing your training set. And we know from Hoeffding's inequality that you have to have a training set of suitably large size in order to get good generalization error. So there's this tension here. If you want a good estimate to see how your hypothesis is doing and make decisions about your hypothesis that you select, such as the regularization parameter to use, based on this out-of-sample error estimate, well, you want a good out-of-sample error estimate. But if it's too good, i.e. k is large, you get better out-of-sample error estimates, but the model you build is going to be very poor, right? Because it doesn't have enough data points. And so dval is going to be that set aside, that validation set, whereas dtrain is going to be that training set that you're going to use to train your model. So if you have small k, this out-of-sample estimate, eval, that's going to be really poor because k is small. That variance is going to be divergent. This out-of-sample error, the validation error, this term here, the deviation is going to be quite large if k is small. And so that means the decisions you make based on this out-of-sample error estimate are going to be poor decisions because it's not going to be very close or very representative of what your real out-of-sample error is going to be. So if you make your k large, what happens? Well, it's a very good estimate and you're really sure how it's going to perform out of sample, but the thing you're really sure about is horrible. So essentially here, if k is large, you're saying, I'm pretty sure that your performance is going to be horrible, which is not very helpful at all. So let's take a look at the relationship between expected error, in-sample error, and out-of-sample error as a function of the number of data points. So here we have n minus k, the number of data points. If n minus k gets larger, that means k is getting smaller. So if we go in the direction to the right on this horizontal axis, that means k is getting small. So this arrow, k is small in that direction going to the right. In the direction going to the left, that means k is big. So we'll just draw that arrow, k, the validation set size, is big. If k is big, that means your training set, this training set here, is going to be very small. And if you have small training sets, well, your in-sample error is not going to be good. Your E-in and E-out are going to diverge because of Hoeffding's inequality. And you can increase the number of data points. And eventually, in-sample error is going to go up, and eventually it's going to turn the curve because then you'll have enough data points. But you have enough data points, well, guess what? K is small. So the decision you make about when to stop training, that early stopping, is going to be a bad decision because your estimate is poor. If you make k larger, well, you're robbing your model. If you make k smaller, you have a bad sample estimate for E out, but that's not going to be E out's going to get smaller and smaller and smaller because the model you train has more data, but your estimate of E out is going to be poor because k is small. So we have a natural tension here about choosing the right k, and there's something we can do about it But at first approximation, at this juncture, there's this competing tension. If K is big, you have good estimates for out-of-sample error, so the decisions you make are based on reliable or more reliable or better information about what E out would be. But if K is too large, well, the performance of your model is going to be bad. And so for your final best hypothesis G, if we go in this direction to the right, well, out-of-sample error is smaller because the number of data points you train on, this G, is going to be a better performer. But when you make decisions based on estimates, those estimates are poor. So there's this tension that goes back and forth between K and between the quality of the final best hypothesis. Okay, so one of the strategies you can employ is to essentially put back in the set-aside data to give the maximum amount of training data once you've made your decision from this estimate. And so the idea here is that, okay, well, you're only making an estimate of out-of-sample error and using that to inform your model choices. But once you've made that choice based on the estimate, you then restore the full-size data set and train it again with that full-size data set. And the idea is that that limited final best hypothesis will improve even more because it has more data. So we start out here and we have this full data set, that's D, and we take our full data set and we split off D train. So we set aside K data points and the remaining K n minus K, we use that to train. Now when we train on this reduced data set, that D train of size n minus K, we're going to get a final best hypothesis. We'll call that G bar, G minus. Now G minus uses this minus symbol because it's the final best hypothesis minus that set aside data. It's not the best we could do, but it's the best we could do with this reduced data set. Now, we took the set aside, and when we get this G bar, we pass the set aside, our validation set, dval, through this limited final best hypothesis G minus. That will give us our validation error eval for that G minus. Now, of course, once we know which G minus is better, maybe we have a G minus associated with lambda equals 0.1. Maybe we have another G minus associated G minus with lambda equals 0.001. Once we make our model choice or selection with this G bar, we will run it through our validation set, and this gives us an estimate of what out-of-sample error would be on this limited final best hypothesis. So once we make a selection about which of these model choices we're going to make, we then take this set-aside data, combine it back with our D-train, get the full data set, take this model choice that we made, and then train it with the full data set. Now we're guaranteed, of course, because this full data set is larger than D-train, the model choice you made, which was the best using this estimate, is going to even improve more, and Herfting's inequality and VC bound tells us so. So what do? We take this D with n many data points, we split it off into D-train and D-val of size n minus K and K respectively. We train using D-train and we get some G minus, suboptimal final best hypothesis. Then we run our D-val, our validation set, through this suboptimal final best hypothesis G minus. We get the validation error, and then we combine back our validation, take the full data set, and train on that model choice that gave us G minus. And because it's a larger data set, it's going to be better, and VC dimension tells us. So if K is small, we're going to have a high variance. If K is big, the difference between this G bar and this G is going to be very large. And the reason why that difference is very large, because this data set is going to be small and this data set is going to be larger. So a small k, small validation, gives you high variance. So that means your model choice is going to jump around a lot, right? This estimate of out-of-sample error is going to be very widely varying, right? So you're going to make poor model choices. But if k is big, you get better estimates on which to base your model choice. But the difference between this limited or the suboptimal final best hypothesis G minus and this better final best hypothesis that trained on the full data set, that gap, that difference is going to be very large. Okay, so the typical value rule of thumb for the size of your validation set is about 1/5 of your in-sample points. Now, some would argue it might be less, might be more. This is just a rule of thumb. And so essentially what you're doing when you're doing validation, you're reporting on something different from your estimate, right? So you're going to have an additional test set, and then you're going to report on it, and the hope is that you choose your K well enough that you manage this balance, this interaction between G minus and G. You manage that well. Okay. So a validation set is not the same as a test set. Let's draw the distinction between them. So here you have your data. That's your original data set. You have your training set, and your training set is what you use to build your model. You have your validation set, is what you use to make model choices to estimate out-of-sample error, and then you have your test set, what you use to examine the performance. So you have your training set that goes into your model, and your model has a number of choices that you can make, right? Now you make that selection for your model. Maybe there are different parameters like lambda or so forth for each one of these models. Your validation set is then fed into each one of these models, right? And based on which one gives you the best eval, you're going to make a selection of one of these model choices, and you're going to take that model choice, you're going to train it now with the training set combined with the validation set, right? So that's G minus, some G minus. You're going to take the training set and you're going to take the validation set, you're going to input them into that G minus, and that's going to give you your final G. So then you take this test set and you run that test set through your final G, and that's your evaluation, and that's your performance out of sample E out. Okay, so a validation set is not the same as a test set. The validation set is an estimate of E out that you use to impact the learning. In this case, you're using eval, right, that performance on the validation set, to choose a model, and it might be a model that has different values of lambda, like lambda equals 0.01, lambda equals 0.1, and lambda equals 1.0, and so forth. And so essentially what a validation set gives you when it estimates out-of-sample error, where eval is E out plus or minus some big O of 1 over radical K, what it gives you is effectively an early peek at what out-of-sample could be based on the current model selection. And so as such, this validation set is not the same as a test set. It's how you would estimate E out as a way of deciding early stopping. So that could be, based on a certain number of rounds or epochs for a neural network. You look at eval at each step along the way, which is an estimate for E out. And once you see eval stop decreasing, and start to increase, then you stop there instead of going through your full set of rounds or epochs for running back propagation on your network. Okay, so when you are selecting from among one or more hypothesis options or model options using this eval, it can introduce this validation set a so-called optimistic bias. That means it may appear that things are better than they really are, right? Meaning that your out-of-sample error might appear smaller than it really is. Because remember, when we said eval was equal to E out plus or minus that proportionality with respect to 1 over radical k, right? That deviation. Now, of course, you have a broad range of what you think E out should be. And on the worst case, you get that minus deviation for a really small k, and you would think that E out is much smaller, your estimate, this quantity is much smaller than it really is. So let's say you have two hypotheses, and let's assume for the sake of example that out-of-sample error for each of these hypotheses is 0.5, right? And so you have the error estimates E1 and E2 for each of these hypotheses, where E1 is the error estimate for H1 and E2 is the error estimate out of sample for H2. Now you're going to pick one of these based on whether or not E1 and E2, which of the two is smaller. If the error estimate for H1 is smaller than the error estimate for H2, you're going to pick H1. Likewise, if the error estimate E2 is smaller, then you're going to pick H2 as a result of your eval, your estimate for out-of-sample error. And so let's assume that these error estimates, if they were uniform on the closed interval 0, 1, because these error estimates could say I have anywhere from 0% error, right, up through 100% error. So these are percentages that talk about your error. And let's assume that ground truth, both of these error estimates were 0.5, right? Out of sample performance for H1 and H2, 0.5. So now what do? You're going to pick some hypothesis from this set that includes two different alternatives, the first version of hypothesis H1 and the second one H2, and you're going to use this criterion of selecting the minimum error estimate. So you're using these error estimates as a way of picking these hypotheses, and each one of these hypotheses have a true out-of-sample error of 0.5. So this introduces a so-called optimistic bias. So what can happen? Well, let's look at the error estimate, the probability that your out-of-sample error for the estimate is going to be less than 0.5. Well, what can you have? If you're going to pick a minimum, that means E1 could be less than 0.5. At the same time, E2 is less than 0.5. Okay, you could have E1 is greater than 0.5. At the same time, E1 is greater than 0.5 in terms of the error. You could also have E1 is less than 0.5. At the same time, E2, it should be 2, is greater than 0.5. Or you could have E1 is greater than 0.5, and at the same time, the error estimate E2 is less than 0.5. So these are the four alternatives that you can have if you're trying to determine what compute whether the expected error of E, your optimal choice, is less than 0.5, right? Because it's either going to be E1 or E2, depending on which one is less than 0.5. So we're looking at this 0.5 condition. So we have four different alternatives, and for 1, check that off, 2, check that off, 3, check that off, the error of your selection, if you're selecting the minimum, is going to be less than 0.5. So that means 3 out of 4 choices, so a total of 75%, or 0.75, is going to be the probability that one of them is going to be less than 0.5. If you're selecting the minimum, you only need one of them to be less, but that covers 75% of the cases. So what does this boil down to? If you're making a selection, then the probability that if you use these estimates as the criteria, the minimum estimate as a criteria for selecting the corresponding model alternative or hypothesis, H1 versus H2, the probability that that E you select is going to be less than 0.5 is 75%. Now, this is an optimistic bias. It means that more of the time than not, you're going to have an error that's less than 0.5, right? And this is certainly very different from what reality is, because they both have an error out of sample of 0.5. But this says 75% of the time is going to be less than 0.5, right? So this is an example of the fact that you have a bunch of alternatives this selection can introduce an optimistic bias, make things look like they're better than they really are. Now, certainly you could just swallow that, because the utility of validation more than pays for this optimistic bias that gets introduced. Okay, so we're going to go next to model selection and explore that, but right now it looks like it's time. So we will stop here, and I will see you online on Tuesday.